Hi everybody, today we are going to be talking about vector spaces and subspaces. This is in section 4.1 in our textbook. And we're going to start off with putting up the definition of vector space here. We did this in class before spring break, and I'm not going to write all of it out while we're on this video. I'm not going to go over all of it. But basically, a vector space, it's a non-empty set, and we call the elements in that set vectors. And we have two operations defined. So we have addition, and then we have scalar multiplication. And we are going to assume here that scalars are always real numbers. That's not true of every vector space, but in this class we're just assuming that's the case. Okay, so we have various properties, axioms that all have to hold in a vector space. It's closed under addition, so that's one that I do want to talk about. So what that means is that if you take something in the vector space and you add it to something else in the vector space, the overall sum is back in the vector space. You can never add two things together and get out of the vector space. And there's a similar thing over here with scalar multiplication. If you have a vector in your space and you scale it, you can never magically get out of the vector space. Okay, so we have commutativity, associativity of addition. We can distribute scalars like we want. So we're talking about, stuff like this. Whoops, that's not a scalar. Okay. There's a zero vector. Everything has an additive identity. You can add something to it to get back to zero, and the scalar 1 acts like we think it should. All right, let's talk about a few examples. So the biggest example of a vector space is one that we've actually been working with, which is Rn, right? So for instance, if we're in R2, you can take two vectors and add them together to get another vector in R2. You can take a vector and scale it by a real number, and you get another vector back in R2. All of those properties above hold for everything here. All right, so let's talk about an example that's maybe not quite so intuitive. So let's talk about here Pn is the set of all polynomials of degree n or smaller. N is a non-negative, let's say n is an integer. Okay, n is a non-negative integer, and we're talking about real coefficients here. So what we're talking about is basically, remember, degree 0 is a constant, and if we're going up to degree n, I'm just going to say that let our variable be called t, okay? So constant term, t squared term, all the way up to a t to the n term, okay? And here the ai's are all real numbers, okay? So let's maybe just restrict to P2, for instance. Okay, so P2, we're talking about things like, 2 plus 3t plus 4t squared, or, negative 1/2 t squared. Or, remember, it says degree n or smaller, so we could also have things just like 1 plus t or 11, right? Things with smaller degree are still in there. And let's remember, right, degree is the largest exponent of our variable here. Okay, so first of all, we have to talk about how do we define our operations before we can talk about if our operations actually fit this definition. We have to talk about vector addition. Okay. Let's see here. So basically, if I give you, if I give you two, quote, vectors in this space, how would you add those together? I'm going to pretend like you all said, combine like terms. So this is just polynomial addition like we've done before. So you add the terms with the same degree. So 2 and 1 gives you 3. 3t is the only term there. And, 3 and 5 gives you 8t, and then 3t squared. Okay, so you're always still going to end up, if the largest degree you have is 2 in either of those, you're always going to get something degree 2 or not. Okay, what about scalar multiplication? Let's see. So scalar multiplication, we want to take a polynomial. So, 6 minus 7t plus t squared, multiply it by a scalar. So let's multiply this by -2. And how are we going to define this scalar multiplication? I'm going to pretend that all of you just said, well, just distribute it. And that's exactly what you do. So we're talking about something that we already are familiar with, which is polynomials and polynomial multiplication. But we're putting it in a new context, a new structure, which is vector spaces. Okay, let's talk about a little bit more, and that is, what would our 0 vector be? And our 0 vector is just going to be the constant polynomial 0. And we can also talk about additive inverses. So if I have, say, 2 minus 5t plus t squared, the additive inverse is what I add to it to get back to 0, and it's going to be what we expect. How do we undo that? 2 with a -2. We undo that with the opposite sign, 5t. Okay, so if we call this u, then this is just literally u scaled by a minus sign. All right, and we inherit all of those other requirements, those axioms, based on just based on these operations, right? They're nice. They fulfill the 10 axioms of a vector space. So there's a little bit of a non-traditional vector space.